In the beginning, the universe was a dense, thick mass that underwent a colossal explosion, leading to the formation of particles, atoms, stars, and galaxies, the elements that make up our observable universe today. This explanation has been widely accepted by physicists for years. However, recent research has presented an intriguing alternative perspective. The universe might not have had a singular, definitive beginning as once believed. Instead, it could be part of an eternal, repeating cycle where the universe undergoes endless phases of expansion and contraction. Brian Cox, a renowned physicist, expresses skepticism about this new theory, arguing that something cannot emerge from nothing. This critical view adds a fascinating layer to the ongoing debate. Furthermore, findings from the James Webb Space Telescope challenge the notion that the Big Bang marked the true origin of the universe. This raises a crucial question. If the Big Bang wasn't the universe's beginning, then what was? Join us as we explore the origins of the universe, examining the boundaries of the Big Bang and uncovering answers to these profound questions. If you're keen on staying updated with the latest discoveries about the universe and its complexities, subscribe to our channel. Hit the like button, share this video to reach more people, and turn on notifications. Scientists have developed a detailed understanding of the universe's early stages, known as the Big Bang theory. According to this model, about 13.8 billion years ago, the universe was much smaller, hotter, and denser. During this period, all the elements that form our reality were created in a matter of moments. In this theory, our universe, including stars and galaxies, was once as small as a peach, with a temperature exceeding a quadrillion degrees. Remarkably, this narrative aligns perfectly with current observations. Astronomers have studied everything from the leftover electromagnetic radiation of the early universe to the abundance of the lightest elements, and everything matches the predictions of the Big Bang model. Despite the theory's strong evidence, we know that it doesn't tell the whole story. There's a missing piece of the puzzle, an understanding of the very first moments of the universe. This challenge arises partly due to the limitations of the physical theories we currently use. The combination of general relativity and high-energy particle physics provides a valuable framework, but as we delve deeper into the universe's first moments, the mathematical complexity increases significantly, reaching a point where our current methods can no longer offer meaningful solutions. One indication of this difficulty is the singularity, a point of infinite density, at the start of the Big Bang. This suggests that the universe was once compressed into an incredibly tiny, dense state, which seems physically implausible. To address this challenge, we must explore new realms of physics, develop approaches that surpass these limitations, and provide a fuller understanding of the universe's earliest moments. Our current tools and theoretical frameworks are not robust enough to tackle this puzzle, so we need to develop new physics that can account for gravity and other fundamental forces at extremely high energies. This is where string theory comes into play. String theory aims to be a unified physical model that can combine gravity with the other fundamental forces, particularly at ultra-high energies. String theory suggests that it can offer an explanation for the universe's first moments. One intriguing idea within string theory is the concept of the erotic universe, named after the Greek word for fire or blaze. This theory proposes that the Big Bang was not the absolute beginning of the universe, but rather the result of a prior event. It wasn't a start, but part of an ongoing process. Building on this, the idea of a cyclic universe has gained attention, proposing that the universe undergoes an infinite cycle of expansion and contraction. This idea, known as cyclic cosmology, was suggested by renowned physicist Roger Penrose, who later won a Nobel Prize. Penrose was intrigued by a profound mathematical relationship between the early universe, characterized by extreme density, temperature, and smallness, and the distant future, where the universe is cold, stretched, and devoid of matter. The theory suggests that these two states could be mathematically equivalent if pushed to their extremes. While this may sound puzzling, Penrose's model proposes that the lack of matter in the universe could actually be the driving force behind the creation of all the matter we see today. From this perspective, the Big Bang originates from what remains after all matter in the universe has been consumed by black holes, which ultimately evaporate into scattered photons in an empty void. In this sense, the universe arises from what is essentially a state of nothingness. However, this nothingness still represents a form of reality, just an empty one. The key to understanding this lies in a complex mathematical concept known as a conformal transformation, which changes the scale of an object while preserving its shape. Penrose demonstrated that the cold, empty state and the hot, dense state of the universe could be connected through this scale transformation, adjusting their spatiotemporal configurations despite differences in size. Penrose argued that in such extreme states, the concept of size becomes irrelevant. In cyclic cosmology, the universe transitions from a cold, empty state to a hot, dense one. The hot and dense state is the result of the previous cold, void state. However, this causal relationship does not follow the typical progression of time, as both size and time lose their usual meanings in these extreme conditions. In this context, the cold void and the hot dense state exist on separate timelines. For an observer within their own time frame, the cold, empty state would seem to continue indefinitely. In cyclic cosmology, physics and philosophy intertwine as the cycle of the universe progresses. Theoretical cosmology offers detailed explanations for the origin of these cycles, but even if Penrose's ideas gain further support, a deeper philosophical question remains. How did these cycles come into existence in the first place? This leads us to consider the profound question of why there is something rather than nothing, a major cosmic inquiry. For the purposes of this discussion, we'll focus on explanations within the realm of physics. There are three possible avenues to explore when considering the origins of these processes. First, there may be no physical explanation at all. Second, there could be an infinite sequence of cycles, where each cycle represents a different universe, and the initial quantum state of each universe is, in some way, influenced by a preceding universe. Lastly, a single repeating cycle could exist in a universe where the beginning of each cycle is determined by some factor of its own end. These possibilities are appealing because they avoid the need for uncaused events and offer more complex explanations within the physical structure. In the field of physics, Roger Penrose proposes the idea of an endless succession of cycles, influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed. Upon observation, the system randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events that cause variations between cycles. This idea opens up exciting possibilities for experimental physicists, as it suggests the potential for detecting subtle traces or anomalies in the residual radiation from the Big Bang, as we continue to probe the mysteries of the universe's origins and its cyclic nature. However, our understanding is at a crossroads between experimental observation and theoretical speculation. The current theory of the universe's origins provides a clear framework for explaining the expansion of the universe and the formation of galaxies, stars, and planets. Yet, it also leaves key questions unanswered, particularly regarding what existed before the Big Bang and whether our universe is just one iteration in an eternal cycle of cosmic birth and rebirth. Recent advancements in cosmology have led to competing theories that challenge the conventional narrative of a singular Big Bang origin. One such theory gaining traction is the concept of the multiverse, where our universe is just one of countless others, all existing simultaneously. This idea stems from theoretical extensions of quantum mechanics and string theory, suggesting that different regions of spacetime could give rise to distinct universes, each with varying physical constants and laws of nature. Within the framework of multiverse theory, each universe may have its own unique history, beginning with its own version of a Big Bang event. This scenario offers a potential explanation for the fine-tuning of physical constants observed in our universe, as it posits that only in a universe with specific parameters like our own could complex structures like galaxies and life arise. However, the multiverse theory remains highly speculative and lacks direct experimental evidence. Critics argue that it may be difficult, if not impossible, to test experimentally, as any interactions between universes would likely be beyond our observational reach. Despite these challenges, proponents argue that the multiverse provides a natural extension of our understanding of cosmology and may even resolve some of the persistent puzzles of the Big Bang theory. Another intriguing area of investigation is the role of dark energy and dark matter in shaping the fate of the universe. These mysterious components, which together make up the vast majority of the universe's mass-energy content, exert gravitational effects that are crucial for understanding cosmic evolution. Dark energy, in particular, is believed to be responsible for the accelerated expansion of the universe observed in recent decades, a phenomenon that challenges earlier models which predicted a slowing or steady rate of expansion. The nature of dark energy remains one of the most significant puzzles in modern physics, with current theories suggesting it could be an intrinsic cosmological constant inherent to spacetime, or it may emerge from more exotic phenomena, such as a dynamic field that evolves over time. Understanding dark energy is vital not only for cosmology but also for reconciling observational data with theoretical predictions regarding the ultimate fate of the universe. In contrast, dark matter presents a different mystery altogether. Unlike dark energy, dark matter interacts gravitationally with visible matter and can be inferred from its gravitational effects on galaxies and galaxy clusters. However, its exact nature, whether it is composed of yet-to-be-discovered particles or is due to modifications in gravitational theory, remains elusive. Solving the mystery of dark matter is crucial for refining our understanding of galaxy formation, structure formation, and the large-scale distribution of matter in the universe. Beyond these puzzles lie broader questions about the nature of reality itself. General relativity provides a robust framework for understanding gravity and the curvature of spacetime on large scales, but it encounters limitations when extrapolated to the extreme conditions of the Big Bang or within black hole singularities. On the other hand, quantum mechanics governs the behavior of particles and forces on tiny scales, offering valuable insights into fundamental interactions but struggling to reconcile with gravity. Attempts to unify these two pillars of modern physics, general relativity and quantum mechanics, have led to speculative frameworks such as loop quantum gravity, quantum cosmology, and string theory. Each of these approaches seeks to extend our understanding of the universe's earliest moments and its fundamental laws beyond the constraints of current observational and experimental capabilities. String theory, in particular, suggests that fundamental particles are not point-like but are rather tiny strings or membranes vibrating in higher-dimensional spaces. This theory aims to unify all known forces of nature, including gravity, under a single mathematical framework. Within string theory, the concept of branes, higher-dimensional surfaces, has led to ideas about the existence of higher-dimensional spaces or realms where universes could be embedded and interconnected. Moreover, string theory allows for the possibility of multiple universes or brane universes within this higher-dimensional landscape, each potentially governed by different physical laws and constants. While still in its theoretical infancy, string theory offers a tantalizing glimpse into a more comprehensive understanding of the universe, where the Big Bang is merely one phase in a complex cosmic ensemble. Philosophically, investigations into the origins and fate of the universe raise profound questions about existence and the limits of human